Okay. Hey everybody, welcome to the RI seminar. It's a total, absolute pleasure to welcome Nima Fazeli here. Nima's an assistant professor of robotics at Michigan, and longtime friend and sort of co-conspirator on many things. Anecdotally, origin story, I met Nima in Chile in like 2017, and I found out he was possibly the only other person like on Earth more obsessed with contact mechanics than me. We like basically argued about contact stuff for like
3 days.
For like hours on end, and that's basically how this started. Let's see. Nima got his PhD at MIT with Alberto Rodriguez, doing really awesome kind of dexterous manipulation stuff. And at Michigan, his work, I think, like what I really admire about Nima's work is that he really spans this range of facets of manipulation, from really basic mechanics to hardware, right? Like with sensors, building tactile sensors, to kind of learning and really good kind of mix of things in there. So with that, yeah, I'm really psyched to hear the talk.
Yeah.
Let's give Nima a big round of applause.
Well, thank you very much for the very, very kind introduction. That was super sweet. And I'm honored to be here to tell you about the recent progress we've been making on dexterous manipulation through vision and touch. Now, before getting started, none of this would be possible without my awesome group. Here's a visual of them. Our kind and generous sponsors, the NSF, Google, TRI, Amazon, Boeing, Ford, and maybe other people. So what is my hope? My hope for dexterous robotics is we have systems in the future that look like this. This is Wally. And here's Wally interacting with the physical world. And it's really building this knowledge, this representation of the 3D world that we can use in the future for dexterous manipulation. You can see he's playing around, there's articulation, there's things moving around. He's almost got this childlike curiosity, and this is what I really hope eventually our robotic systems will have. Now, towards this dexterous manipulation, what I think are the key ingredients are sort of these three ideas. I think, or I really believe in 3D or 4D physical representations. I believe in the object centricity and multimodality. And so with these sort of three big ideas, this is generally what a typical robotic setup looks like in my mind. You have vision coming from this view, you have tactile feedback from the tactile sensors, you have some object and you're interested in some forceful interaction with the environment. You want to use a tool, you want to do something interesting. And so for you to be able to do dexterous manipulation, I think you need to understand touch. How do you think about tactile sensing? How do you think about tactile feedback? How to use vision and touch to build these multimodal object-centric representations? And finally, how do you use these things in the context of planning and controls? Now, with these three ideas, these sort of forms of these pillars of my research program. And for today, my hope is that I can convince you of two ideas. One is that I think tactile sensing is really becoming a technology very rapidly. It's very cool. It's very easy to use. I hope to prove that to you, and hopefully you will adopt tactile sensing more and more in your research. And I also want to convince you that sort of model-based methods are still cool. They're still powerful, despite the hype, despite Twitter, despite LinkedIn, despite the billions of dollars that people are claiming. And so towards the first goal, let's think a little bit more about touch. I want to talk about the importance of touch, thinking about tactile perception and controls, thinking about generalizable tactile representations, and finally, some tactile hardware. That last part will be kind of short. So in terms of importance of touch, I really like this visual. This is the creation of Adam by Michelangelo. As with great art, you're going to take away what you will from this. What I take away from here is this notion of centricity of touch, right? Here, right in the middle of exactly, as with great art, you can take away whatever you want, right? Here, what is really interesting is that touch is like very central to this image. If you don't like this sort of more sort of historical take on the importance of touch, it's interesting to note that touch was evolved before your visual cortex was as deeper in your brain. Vision is a relatively new addition, and if you don't care about history, you don't care about biology, then touch has lots of practical applications, right? You can do slip detection, you can do sort of grasp force modulation, you can do shear force estimation, you can do object localization, and something that's quite popular in sort of medical applications is palpitation. This is sort of what you do with your skin to infer whether you have some lump or something else. And so given all these applications of touch, its relative importance, what are we trying to do? We're generally interested in enabling tactile-driven sensory motor skills. So Just to give you an idea of what I mean by tactile sensing, here's a Toyota soft bubble. This is an example of a vision-based tactile sensor. So here there's a camera behind this tactile sensor. It's looking at this membrane, and here Mikkel, he's just poking it with his finger. And you can see that basically you convert this deformation in the membrane into a point cloud. This is why we call it a vision-based tactile sensor. You're transducing a mechanical phenomena into something that's digitizable into an image format. And what we're really excited about is how do you get this sort of a feedback and produce behavior? So in this example, we're not allowed to have food in our lab, so pretend those blocks are food. Okay? So we want to go from that to that. So how do we start to formalize this kind of a problem? How do we start to write down some equations that we can do some controls with? And so the problem formulation typically looks like something like this. Here's my robotic setup. My action space is the end-effector motion. I have access to wrench the wrist. I have access to the tactile sensing, here represented by P sub t. I have access to some representation of the object, Z sub t. It could be an embedding of the point cloud. It could be an RGB image. It could be text, whatever you like. And what I'm trying to do is I'm trying to minimize this cost function. If you're into optimal control or LQR, this should look very familiar. What I'm trying to do is minimize the object-centric features that I care about, so pose and the forces, with respect to some goal, desired value. And I want to do this subject to penalizing some robot actions. I don't want to take crazy robot actions. Now, I need some constraints. There are two types in this problem. The first type is sort of the tactile dynamics. In the modern nomenclature, you'd call this a tactile world model. Do with that what you will. Historically, we've just called them dynamics. So what you're doing is you're consuming the current point cloud measurement, you're consuming the current force that you're feeling, the action you're about to take, and some representation of your object. And you're just trying to predict into the future what will be the future tactile sensation you're going to feel, what will be the future force you're going to feel. In addition to that, you need to compute from these tactile representations what are your object-centric features. And so you have some observation model. This is computing Q sub t, for example. Q sub t is your configurations, the things that you're trying to control. And this modular design is really nice. It gives you the flexibility for task specification. Just by changing the cost function, you can produce different behaviors. It's also pretty modular in the sense that you can kind of switch out the different dynamics modules and observation modules as things get better over time. That's a pretty nice feature, I think. And it offers you this ability to think about tactile world models in a more general sense. Now, with this kind of an architecture, you're going to put this into a pretty sort of a familiar-looking controls loop. We have our controller. In our case, it's always going to be MPC. We're always going to be dealing with under-actuated dynamics. We have our membrane dynamics. This is my measured current membrane state. I can use this to make predictions about how the membrane state will evolve as a function of time, conditioned on the actions that I take. And from those future evolutions of the tactile signature, I can compute positions, object poses, forces, and whatnot. And basically what I'm doing is I'm searching the action space to find future tactile representations that look like the things that I want. So how does an observation model look like? Here's sort of generically what you might cook up. You can also learn these representations. So the idea is that you have some deformed depth map. You can reconstruct these 3D point clouds. You can compare them to your imprints, your initial non-deformed point clouds. You can get these detected contact patches, and you can perform things like constraint ICP, using knowledge of the external world and so on. This is just one approach. You can learn these as well if you like. This is kind of a paradigm works really well. To prove to you that it works really well, here are systems that are running relatively fast. On the left-hand side, we're inferring the pose of this sort of a pen-looking thing. On the right-hand side, we're simultaneously inferring the pose of the spatula and the extrinsic contact with the environment. And I don't mean to position this as research contribution. These are pretty much established pipelines. You can run these things at about 10 hertz. They work really, really well for rigid objects. They're good at doing extrinsic contacts, and they're relatively well established. So really, you can use our repos. You can make up your own repos. These are super accessible. They're very, very good tools. You can just build off of these tools. In terms of our tactile dynamics, this sort of looks like the modern-day world models things. Everything on the left-hand side, that is our current observation. So we're observing tactile signatures, wrenches of the wrist, even sort of proprioception of the arm. We have access to some representation of the object, here a point cloud. You can get a point cloud embedding. You have your robot actions. And what you're going to try to do is predict all those perceptual feedbacks in the next time step. Really, the tricky part here is learning good tactile encoders. Those are basically taking in images and trying to predict images. And so there's a lot of pre-training you can do here. One popular technique is to do something like a VAE. You can use VITs that have been pre-trained on other kinds of images, and all those work relatively well. And once you have your dynamics, you have your perception, you wrap it in your MPC controls, and this robot is completely blind. It's handed the spatula in this configuration right now, and it should be in the green configuration. Everything else is MPC, and the robot is blind. Ta-da, and it can kind of do this for all kinds of spatula-looking rod-like objects, a whole bunch of them unseen in the past. It works relatively reliably well. Another kind of task you can do is drawing. This is kind of a fun task where you constrain the task to be kind of difficult. Here, you're not supposed to lift the pen ever, and you're just supposed to draw the longest straight line you can. And with these sensors, one of the failure modalities is shear out of the grasp. And so the robot has to work really hard to continuously adjust its grasp to keep drawing. The goal is to get to the end of the salmon line if you can. And funnily enough, it's a nice benchmark. If you can get to the end of that line, you're probably beating everyone else. So if you're interested, drawing a 1 meter long straight line is super hard. Now you can say, okay, drawing in-hand pivoting, those are not that fancy, show me something else. Here's dense insertion. The robot takes a first image and then it's blind again. Here the environment complies, and so it has this sort of understanding that the environment may comply if I apply forces. Here it's doing simultaneous in-hand object pose estimation. It's doing extrinsic contact estimation, that's that sort of red cylinder. And then it's also trying to estimate where the blocks will move conditional on the actions it's taking. And once it creates a cavity it thinks is big enough, it's just going to try to jam this thing in. And it's going to keep trying to do this over and over again. Again, this is MPC. It's just like pretty sweet. And kind of example applications of where you might want to do something like this is in the context of big logistic companies like Amazon. Maybe you want to put things in boxes, dense insertion. You might want to do this in your kitchen. You might want to do this with books in your bookshelf and so on. It's pretty cool. And some of the most dexterous capabilities we've come up with is truly manipulating something that is not within your grasp. So here, what I want to do is take this polygonal object on the table, and I want to make it balance on a corner. And what I'm going to do is hold something in order to do that. So I'm going to hold this little box. I'm going to use the box to try to pivot the object, and it can be any polygonal object. And you can get to balance on the corner kind of nice. And some of the challenges here is that there's frictional interaction between the box that you're grasping in your fingers. There's frictional interaction between the box and the object in the environment, and there's frictional interaction between the object and the ground. And you have to worry about this extremely underactuated system. Balancing it is quite a challenging task. And we can go again. And what's nice is, again, a relatively simple, sort of straightforward sort of a learning method for the tactile dynamics, some planning, and life is good. So have we solved the tactile perception and control problem? I would say definitely not. There are some issues to address. So both in the context of the observation model and the tactile dynamics, there are some issues. So one idea is geometric aliasing. This is an artifact you get in the observation model that will make the estimation of pose in the hand quite difficult. You need to worry about generalization across sensors. So I showed you results on the bubbles. I didn't show you results on any other sensor. So we should worry about that. Then there's the idea of tactile shadows and generalization across embodiments, which I'll get to briefly. I think kind of the most technically interesting one is the geometric aliasing idea. So if you're purely in the tactile domain, here's my robot. It's holding a rod. S1 is its initial state. S3 is a state after it takes a 90-degree rotation. So it's grasped, let go, did a 90-degree, and then grasped again. X1 and X3 correspond to the tactile signatures in the first grasp and the second grasp. And what you can see is there's like a little rod thing in the middle, and then I can see the top of my rod in the second one. Now, for the exact same behavior, so that 90-degree rotation, but now I'm going to do the grasp much further down. Now I'm holding the rod much further down, and I do the same 90-degree rotation. The observation here is that X2 and X4 look shockingly similar, and X4 does not look like X3. So even though the first image, the first perceptual feedback is the same, the action is the same, the outcome is different. And so this is what we refer to as a geometric aliasing problem. And if you take a traditional encoder-decoder approach to this idea, what you'll observe is that as you try to embed these observations into some latent space and then decode back out, what's going to happen is you're going to get your latents kind of covering each other. Your model's going to be blurred. It's going to try to predict the average of these two outcomes. And so this is kind of a pain, especially if you're trying to do controls, in the sense that you need to have sort of a prediction of which one's going to happen. It kind of needs to snap to one of these predictions. And so before generative modeling was like a very hot topic, decoder-only methods were a hot topic. And so here's a decoder-only approach where the top one you read from left to right. When you're learning decoder-only architectures, you read from right to left. We start from our latent space. And what we're trying to do is we're going to try to decode a latent space into observations and also decode them into future latents. And so the way that we do this is, OK, given some distribution that I'm sampling from in my latent space, characterized by mu and sigma as a Gaussian distribution, what I'm going to try to do is decode into my tactile observation. I can also try to predict future tactile latents, here mu2 sigma 2, all the way to mu t sigma t. And I'm going to impose, in this particular case, linear latent space dynamics, so A and B. I'm also going to learn A and B. Those are going to be part of my parameterizations. And so in this problem, I'm learning my decoder, I'm learning A, and I'm learning B. If I do this correctly, then I can actually decompose or decompress these overlapping latent representations. If you go ahead and do that, here is our way of demonstrating how well these things work. This is the tactile cart pole. If you're a control theorist, you're going to be really in love with the cart pole problem. This is our take on the cart pole problem. We have a cart. It's got a pole. You yank the cart. The robot gets annoyed. It has to make the rod go upright again. You yank it again. The robot has to try to make it upright again. And this is sort of a very similar problem to the issue that we were having in the past, where you have just geometric aliasing effect. If you do a good job of figuring out your aliasing, you should be able to keep this upright. We can keep it upright for about 5 minutes. With an encoder-decoder only architecture, it drops it within about 10 seconds. So it has like a huge impact here. This is sort of a more controlsy task. Again, tactile cart pole is pretty cool. It's a fun little baseline. We can also do sort of purely perceptual tasks. So here is a robot. You hand it a variety of different objects, again, somewhat aliased, and it has to figure out, OK, how should I move my end-effector such that I can make this object horizontal? And so this is like a nice tool. I think that there are probably other ways to address geometric aliasing using more generative models, maybe modern tools with diffusion and so on. And it'd be an exciting direction to move in. But I want to sort of switch gears and say, so let's talk about generalization across sensors. So suppose I had a bunch of really cool models that I've developed for my tactile sensors. And now someone comes along and gives me a new sensor. So maybe our gel slims or the Digit 360, the cool work from Meta. And the question is, how can I, without recreating my algorithms, so my controls algorithms and my perception algorithms, achieve the same, at least, perception capabilities, right? So I don't want to retrain everything from scratch. I don't want to reproduce everything. That's a huge pain in the ass. I don't want to do that. And so this is the kind of thing that I want. I want to be able to design capabilities for the left and then realize them for free on the right. The distinction between these two is that the left is the bubble and the one on the right is a gel slim. And I want to be able to do that for free. I'm going to show you two kinds of approaches we've come up with, and I'm sure that if you get excited about this topic, you'll come up with your own. The first is our touch-to-touch framework. So in touch-to-touch, what we're going to do is we're going to say, OK, I have this signature from this new tactile sensor that I don't know what to do with. What I can do is I can map it to what it would look like as though it were collected by the other tactile sensor. Then run all my perception algorithms and then behave as though it has been grasped by the one that I know what to do with. And so to train such a representation, you're going to collect a data set of spatially aligned tactile signatures. So the top one is showing you the data set, the same sort of object that we're grasping with the gel slim and the bubble. Those are the signatures. So it's the same object. I'm grasping it in the same configuration, but with two different kinds of sensors. I collect this sort of spatially aligned data. And as you do with diffusion models, you just throw it in there and you train a really cool diffusion model. It's a model that will basically paint one signature as though it's collected by the other camera, by the other sensor. And so here's some baselines. There's the ground truth. There's our tricks that we play to make diffusion work well. There's VQVAE, there's L1, there's FISGel, all these other baselines. But the main point is that you can do really nice reconstructions. Once you have such a model, here's how you would use it. So this robot doesn't know what to do with signatures from the gel slim, but it can convert them to the soft bubbles. And so here we handed a little plastic cup. It gets the signature, converts it over, does pose estimation, figures out, oh, I have to realign it this way, and performs. Oop. Oh. It's frozen in time. OK, anyway. And so, OK, touch is a pretty good idea, but you might say, OK, this is from just one sensor to another sensor. That's not very satisfying. Maybe I have other sensors that I need to map to as well. So an alternative is to say, OK, if I am willing to collect sort of spatially aligned data, then what if I could learn a shared representation across my tactile sensors that I can decode from? And so one approach is to kind of steal ideas from contrastive learning, like clip models, and say, OK, when two tactile signatures are spatially aligned, I'm going to force them into the same latent space. When they're spatially in different configurations, I'm going to push them apart. And so the only thing that I'm going to do is I'm going to learn my perceptual model from the latent space. And I won't care which sensor gave me the particular latent. That doesn't really matter to me. My perceptual model just consumes the latent vectors themselves. And so in this task, the robot, again, has not seen, doesn't really know how to sort these objects from the gel slim, but it does know how to sort them from the latent space. And so it's going to get these objects. It's going to be like, oh, this feels like this thing. I'm going to put it in this hole. We've colored them to kind of give a visual cue of how they should be arranged. So it was only trained on the soft bubbles, and now it can kind of do everything with the gel slims too. Cool. And now you might say, OK, spatially aligned tactile signatures are quite hard to collect, but in our experience and also in the baselines of these papers, they often work much better than not aligned data. And so we have some evidence to suggest this is true. I'll refer you to the paper. Now, I just want to briefly touch on tactile shadows too. Here is a soft bubble. It's touching some object. Here's a signature, and you'll look at this and be like, I can kind of see a T, but there's all these other sort of artifacts here too. And these other artifacts are going to make your pose estimation algorithm sort of suffer. It makes everything a little bit more difficult. And so would it not be nice to just have these artifacts gone? It would be, right? And so one idea is to do something called tactile neural derendering. So the idea here is I give you a tactile imprint, and what I want to do is I want to erase the tactile sensor completely. I want to render the scene as though it was collected by the camera that is looking at the tactile sensor, but without the tactile sensor being in the way. So I want to directly reconstruct the 3D geometry that I was looking at when I touch something. And so that's what tactile neural derendering is. We're going to take the tactile signature, get rid of the tactile sensor's membrane, reconstruct the 3D geometry. And so the way that you train such a model is, in the real world, you'll collect a small data set of interactions between the sensor that you have and the environment. You set up a very, very simple, super stupid simulator that is like very, very coarse and super cheap to set up. You train your diffusion model where you're going to consume tactile signatures. You're going to basically render out the tactile membrane. And you can basically, from here, have the direct access to the 3D point cloud. And from that, you can do fun things like pose estimation. What I want to highlight here is the value of sim. And that is really in the lower table. If you just use the real data, you do relatively well. And it's much better than using the baseline models that we have access to. But by incorporating synthetic data, even if it's pretty crappy, it's not very good, you get a dramatic improvement in your in-hand pose estimation. And so that's a super sweet deal. So now that we know how to deal with generalization to some extent across tactile sensors, we have a good idea of how to remove tactile shadows. We have some ideas about removing this geometric aliasing idea. As with any group dabbling in tactile sensing, we had to make our own. This is the GelStim 4.0. These are super cheap. You can make them for about in the order of like $50. Super easy. They're kind of in many ways similar to the digit sensor. They're very reproducible, they're very reconfigurable, and out of the box they have a bunch of capabilities. To kind of illustrate to you the fidelity of these kinds of sensors, that's the Michigan M. That is an American dime, I think. It's about a coin about yay big. And that is a signature from taking that M, little teeny tiny thing, and jamming it into the sensor. And you can see you can like basically reconstruct the full sort of geometry really well. The kind of software package that we offer you is sort of out of the box depth estimation and shear estimation. Now with Sparsh, I think you have a lot of this stuff as well available to you. Akash, you had to swipe arts. Now you might say, okay, tactile sensing is cool. I don't want to spend this time doing tactile sensing. What else can I do? Audio. Here's audio as touch. And so the idea is I have in one fingertip, I have a speaker that's basically yelling. And I have in the other one a microphone that's listening. And depending on the object you grasp and how you manipulate it, these audio signatures will change. And I know Jeff is sitting there agreeing with me. Look at that. He's done some really awesome work in this space. And so it's a really productive thing to try to do when you have sort of heavy visual occlusion, you have different surface types, you are near contact, and visually it's hard to tell whether you're in contact or not. And so what we do is essentially apply sort of a chirp signal. This is a sweeping signal of many frequencies through the speaker. We listen to it, and we convert the thing into a spectrogram. Always convert to spectrogram is my takeaway from doing anything with audio. There's really powerful pre-trained models that you can use with spectrograms. And it's a pretty simple setup. You have your visual feedback in terms of depth. You have your audio feedback. You fuse them together. And in this case, we're trying to do extrinsic contact estimation. So we're painting a contact probability map in the image. We're saying in this image, this is where the contact is being made between the object and the environment. And here's also like a snapshot of the kinds of results you get. We did a lot of work on sim to real to sim. Real to sim to real. Oh my God. And so here's some examples where you can basically estimate where the contact is being made with the environment. Now you might say, well, that's pretty cool. Audio as perception is pretty cool. Can you go beyond that? And maybe some work that we have under review right now is audio as a actuation modality. And so in this case, this robot essentially has access to the same things. It has speakers in the finger, and they're going to just yell. And when you turn them on, you can make the object move. It's pretty cool. So we have a planning and modeling kind of an approach to making objects move in the grasp with just like yelling. And it's really not that loud. I'm making it sound way more dramatic than it is. So I'd say, OK, quite briefly, I would say perception we've made a lot of progress. In hand object pose estimation, I would say, if it's rigid, it's largely a solved problem. Shear estimation, I would argue, is definitely a technology at this point. There's very powerful methods of doing shear estimation. Extrinsic contact is really getting there. In terms of controls, I think that tactile rigid object manipulation is making a lot of progress. There are many groups working on this idea right now. There's a lot of room to make progress in terms of deformables. I think deformables is wide open. I think David's doing some really fantastic work on deformables. I'm excited to see you do tactile stuff too. It's going to be great. And I would say you have access to lots of different hardware. The Digital 360s that Akash knows a lot about sitting over there. Gelson 4.0, gel sites, soft bubbles. I'm personally not that excited about making the next generation of tactile sensors. I'm also not sure if the next generation will be vision-based. So don't look at this and be like, vision-based tactile sensing is the be-it and end all. It might change, but hardware does not feel like it's the best place to invest time. Now, I'm going to try to be a little brief and talk about the second goal, which is to convince you that model-based methods are still cool and still powerful. And to kind of do that, here's my little Wall-E image. He's interacting with some deformable or some compliant object. What I want to show you is capabilities like this, where you can take a sponge, jam it into like a mug, and try to figure out just from this view that you have access to, what is the deformation, the full 3D deformation of the sponge, and what is the contact patch with the environment. And here's a chain that I'm manipulating, and despite the heavy visual occlusion offered by the cheeses and the mustard, you can still reconstruct this full 3D geometry, and even when it rests on the table. And so where might this have any sort of application? I think tool use is really where you care about this kind of an application. And here's some examples of tool use. And I like to tell this little story of tool use is often for two reasons. It's for morphological change or for safety. Morphological change means I want to turn the screw. My fingers can't turn that screw. I should use something that helps me turn that screw. Or I can't scrape things with my fingers or my nails, or I don't want to. I can use a scraper. Or sometimes you don't want to burn your hand, and so you use a spatula. Maybe you don't want to contaminate your food. Okay? So how to think about object-centric representations in the context of tool use? It's really a story of geometry and force. And so the way you can think about geometry is there's a collection of points. These points belong to the tool. And depending on how these points behave, I can categorize tool behavior. Generally, tools are deformable. That means these points are allowed to move with respect to each other, and there are not that many constraints for them. Or they're rigid. Rigid means these points are allowed to move in 3D space, just not with respect to each other. And there's this like really sweet spot in the middle, which is compliant objects. These are objects for which these particles are allowed to move with respect to each other, but they're governed by Hookean laws, like elastic laws. And they'll bounce back if you remove the external force. And what makes them really cool is that you can have these contact formations that you can control. You can do a very nice force transmission because of the compliance. And there's some deformation which makes them favorable and interesting. The spatula is my favorite example. I think my lab has spent $450 on spatulas up to this point. We love spatulas. They're awesome. And so, okay, how can we think about these objects, these representations? So here's my object geometry. I can also kind of think about the forces transmitted to the environment. I can think about the robot action. I can think about boundary conditions. I can think about the evolution of these things in time. And I'm going to wrap them around this implicit function. I do this very explicitly just because you cannot resolve force without future deformations and future deformations without force. They have to happen at the same time. And looking at this problem, it's nonlinear, it's high dimensional. It's really hard, especially in heavy visual occlusion. And so for our context, what we want to do is we want to predict future object deformations and forces transmitted. I have access to this partial view, so I get to see a subset of these points. And inference means I want to basically look at this model and figure out what the full point cloud is and what the boundary conditions were. So where did I make contact? How does the contact look? And I want to make predictions. How will I deform in the future? What will the forces in the future? Conditional on the actions that I want to take. And so the way that we're going to do this is by taking inspiration from 3D graphics. So in 3D graphics, there's these things called signed distance fields. Here's a Stanford bunny. This is ripped right out of J.J. Park's paper on deep SDF. You can imagine that for every query in 3D space, I can assign to it a value that is greater than 0 outside of the bunny, less than 0 inside the bunny, and it's proportional to the closest point on the surface of the bunny. And so people have shown that you can train these models to basically consume a very large data set and predict really quite good signed distance values. Now, this is the problem we have. This is a simplification of the problem that we have where the object is not deforming. There's no sort of force transmission. There's no boundary conditions. There's no actions. If you take a look at this third line is what deep SDF does. It assigns to every single point a distance value. And so the question is, how do we work our way back? How do we put back in 3D geometry when the object is deforming? How do we put back in force? How do we put in action conditioning? How do we put in boundary conditions? And the key insight in all of this story is this slide. On the left is my tool in two configurations. The far left is there's no deformation, and then the next one is that I've taken some force and applied it to it. Now it's sort of deformed. The signed distance field that you're seeing, this is the nominal shape. There has been no deformation applied here. This is just a slice right down the middle. Blue corresponds to outside and far away. Deep red is inside the thing. And so, okay, if I apply some contact, I deform this thing. This is a deformed shape. Okay, and what I want to do is learn a vector field that will take the second one and map it back into the first one. And what I'm going to do is condition this thing on forces, actions, and the boundary conditions. That's sort of the key sort of idea. The rest of this story is an implementation. We have over the years several implementations of this idea. There's a force module that will produce these force codes. These will modulate the way that the deformation module works. Together, they will come together to predict these like vector fields. You apply the vector fields of deformed geometry, you recover the original geometry. That S in the end, that's your SDF. And you can make these action conditions, so you can have an action module that will produce future versions of this. If you go ahead and construct this, collect some data, so here's my robot play data. You basically get robots to grab $450 worth of spatulas and chains. You have it knock around. Then you get these kinds of capabilities. So here is my robot. It has a spatula. It's trying to serve peas. And on the right-hand side is the raw sort of point cloud feedback. And what you can see is that despite heavy visual occlusion, that sort of magenta color is a reconstruction of the full spatula's geometry despite heavy visual occlusion. So you can see, especially when there's like holes in the point cloud, you can see that the magenta kind of like shows up. We can basically track where it is in 3D space really reliably. We can track the contact locations. We can predict future forces. We can do this for chains. It's pretty cool. Here's a chain example. So bottom left is the raw visual feedback again. The main idea is that the chain is heavily visually occluded. Now I think the most interesting thing here is how does state estimation work? And it's a little bit atypical compared to traditional sort of inference in one pass, forward passive neural networks. The way that things work for us, especially in the context of partial views, is that, so suppose this is my undeformed object and I deform it. But this is the view that I get, that cone. That corresponds to this view. So given just this view, that wrench feedback, and my robot configuration, how do I do inference? So the main idea is to think about this representation and freeze everything except C sub t. That is a representation of the contact formation that you have. Everything else is frozen. And what we're going to do is we're going to do backprop over the partial point cloud into that C sub t. And if you keep doing that and updating your belief over C sub t, over a period of time, you're going to go from your initial guess, which is the sort of like bluish color, to the ground truth represented in magenta. This is some of our older work. It happened at about 2 hertz. Our more recent versions run at about 10 hertz. So it's a little bit atypical. You do this sort of inference via optimization approach rather than just forward passes of neural networks. It's a little bit more expensive than traditional approaches, but it is quite tolerant to uncertainty. Now, something that's really cool about this kind of representation learning is that you get some things for free. So in this case, we get dense correspondence for free. There's no supervision here for dense correspondence at all. What we're doing is painting our spatula as this sort of rainbowish color. And what I'm trying to indicate is like, where do these colors migrate over time? Now, if you're Zach and you're looking at this, you're like, what about that one on the last? Yeah. On the right, sorry, yes, that one. Your correspondence looks like it's not very good there, and you're right. So the main idea is that there is an inherent bias in our model towards having minimum length vector fields. So points don't actually follow true displacements. They kind of take the shortest path they can. And so if you have twists, if you have like really long bends, it's not great. I have never seen a spatula in that configuration yet, and we've done lots of experiments, so I don't know how worried I am. We've continued this line of work with NDCF. This is our riff on the NCF idea. We're looking at sort of doing this thing on simultaneously estimating contact in a more explicit way. And so this one was really neat in the sense that we trained it entirely in sim, in Isaac, and we did zero-shot sim to real transfer. So you take this sponge. We were really interested in sponges because kitchen tasks, and we just jammed into a whole bunch of different things. You train your model. Here are some examples of the partial point clouds we got in sim, the reconstructions from our model, the baselines, and then sort of the ground truth. The idea is to say, hey, it works in sim. I think the thing that was the most interesting to me is how do you evaluate contact patch estimation in the real world? Here's what we did. It's an acrylic plate, and you literally just take your sponge and push it into the acrylic plate and have a camera look at it. So the Photo Neo is an extremely high resolution, very high-end camera. It reconstructs point clouds. It's almost like you simulate them. It's like really an amazing investment. I would recommend it. And we can basically see like exactly how the thing is deformed and get ground truth evaluation for contact patch. Obviously, it only works for flat things. We haven't really tried making acrylic bend or anything, but at least in the flat context, we have ground truth. And so here's the partial views that we have access to. You can see that we get very little of the sponge. It's really just like two faces of the sponge. And yet we're still able to basically do pretty reasonable 3D reconstruction and contact patch estimation. And you can do it on relatively complex objects. We don't have ground truth for the mug, unfortunately, but sort of it passes the eye check. I kind of look at it, looks good. So the yellow is the reconstruction of the full 3D geometry. The red is sort of the contact patch. Good. And so it works on a variety of different objects. Here's the YCB bow. Again, you can go ahead and interact with the YCB bow. Works pretty good. And so these ideas can be generalized to more sort of sophisticated settings where you might want to do contact control. So if I can estimate where the contact patch is, how do I do some sort of reasonable controls with it? This was our work called calamari. The main idea is that I want to represent tasks as a sequence of contact maps, if you will. And what I want to do is implicitly tie them to the geometry of my robot. And so this is an example of sweeping. What we're going to do is we're going to try to track these contact affordances. These are realized by VLM. Good. And so we train this thing in sim, and we can zero-shot transfer it to the real world. Very nice. And we can sort of generalize across a whole distribution of different dustpans. In this particular case, it's a sweeping task. You can train it for other tasks. So here's sweeping. We can show wiping tasks, button pushing tasks. Again, you can learn something in sim. So these contact patch trackers, and then realize them in the real world. Now, so a little bit of a summary is that I think that we've really got a very powerful tool for elastically deformable objects. I think it works really reliably well. There are approaches that will work for articulated objects. The ones that I can think of are this one from Angju Kanazawa's lab. I think this was with Ken Goldberg. It has a really cute name, Robot See, Robot Do. Pretty cool. And this is some work from, I think, Dieter Fox's group. So yeah, for articulation, I think there's really good progress. For elastically deformable, there's really good progress. I think currently we're stumped on plastically deformable, so Coke can, crushing, Play-Doh. Don't know how to do that. And very deformable objects, so cloth and chains and things I think Dave has a lot of experience with. It seems like graphs and point cloud representations seem to be better things for those than these kinds of ideas. And so I hope I've convinced you that tactile sensing is a technology. It's really cool. It's easy. You should use it. And I've convinced you that sort of model-based methods are still cool and still powerful. And so to kind of wrap things up, this is generally the paradigm I've traditionally thought in, which is your sort of classical controls architecture. And everything I've shown you today has been in these two kinds of, these two sort of quadrants, if you will. There's been models and representations, there's been perception capabilities. And I'm really fond of this idea of causal and feature-rich representations. Causal meaning that they have this ability to explain and predict how things will evolve in the future. I don't need them to be interpretable to me, I just need them to be causal. I also care about feature richness, so things that describe contact and forces and geometries. They're not very pixel-centric or point cloud-centric representations. They have this stronger notion of what objects are and interactions are. Now, this work sort of lives in a world where we have access to things that you see coming out from TRI, these large behavior models. You see work from Marco Hutter's group, these teacher-student distillation approaches with RL and SIM, students in the real world, whatnot. And this like really cool work from Davide's group on aggressive flying with deep RL. And so these things kind of throw a lot of this out of the window in some sense, right? They're essentially pixels or torques kinds of ideas. And so a little bit of a retrospective, 20XX, I would argue maybe in 2013, 2014, we started to ask ourselves the question of first principles versus learning methods. I think for manipulations, from a manipulation perspective, this is no longer really a question. I think learning is here to stay. It's not really going to go anywhere. 2021, forever maybe, is the question of like, do we do raw sensory feedback versus abstract features? I think that is the question in everyone's mind these days, at least in my community. And so it's trying to answer this question of, will there be a bitter lesson in robotics? And if you're not familiar with the bitter lesson, it's an argument made by Rich Sutton, that is saying scaling and compute are going to be the solution to everything. Just forget about human expertise. Every time you've thrown in human expertise, it's just slowed things down. And maybe what I would say is planning is a search, so it's not violating Richard Sutton's opinions at all. And you will eventually need to plan at some point, right? You're not going to see everything. It's impossible, right? So you're going to need to plan at some point. I think that abstract features, these things like geometry, contacts, and forces, are really useful inductive biases, even if you just learn them. I think of these as the CNNs to the MLP that people are using. And the future is probably going to be some fusion of these like large behavior models and edge planning. You're not going to get out of that, I think. And there's really an important difference between understanding and doing. Often when you ask someone about their capabilities, they will try to explain to you why they can do things, not just show you how they do it, right? And I think there's an importance there, there's some sort of causal understanding there that we should value. And with that, I'm going to wrap up. Thank you to my awesome group again, and time for some questions. Yeah, please.
Great talk. Thank you so much. For some the work on estimating contact, that's all being done from pixels, right? You're not using any force feedback when you actually do the inference?
For all of them, there's force feedback from the rest of the...
robot.
Yeah, from the rest of the robot.
Okay. Have you looked into some of the stuff of like just pixels? Is that doable with once you have the force feedback supervision? Or do you kind of need force feedback in order to estimate those kinds of things?
It's really hard to do without force feedback, especially in vision occlusion. And I would actually say the opposite. If you have force feedback, you're like 80% of the way there.
Okay.
It's like really, really informative. And the reason why it's informative is not super surprising. Like if I have a force torque sensor here, and I apply like a force down, I'm going to generate a force this way, and I'm going to generate a torque. And if the object is convex, you're done. You actually have like a precise point contact estimate of this patch. So it's super duper informative, much more so than vision in many cases.
Is that conditioned on having a full model of the object too?
You don't need a full model. You kind of need like a wonky-ish model. Even if it's like an ellipsoid you fit to whatever you see, it won't be terrible.
Okay.
Yeah, but the better your model is, the better it will work. But so the way you can imagine is like if I just draw like a little rod extending into infinity, I can tell you on that rod where that point is.
Provided you know the rod and the surface you're contacting too.
The surface you don't need to have. No. There's a really cool paper called CPF, the contact particle filter. It's a work from Russ and Lucas Manueli, who actually have like an algorithm to do exactly what I'm describing, sort of like very algorithmically. But like the intuition is that if I assume that the force external to me is coming from just a point contact, there's no torque space allowed to apply, and it has to live within the friction cone because like it has to, then it has to have a single uniform resolution on the exterior of my object. It will always penetrate twice, but only one will count because the other one will require contact pull.
Yeah. Thank you.
Yeah, thanks. Oh, yeah.
So for like your spatial experiment, like you did most of it, like collected most of the data in real. I guess, is there like, what are the limitations you see for simulating, especially for some of the more difficult, like deformable objects? And do you think that it'll likely like be faster or better to invest in just doing real world experience for deformables, or to try this in sim?
That's a really great question. I think what we learned, again, things are just evolving so fast. I have a hard time keeping up with everything. But when we started, sim kind of sucked. And then by the time that project ended, sim was kind of doing something. So the following projects use sim, and I've liked Isaac and I've liked Drake. Isaac has been really good for sort of a lot of the deformable object stuff. It's also pretty fast. I do recommend that as a go-to. Drake is really good. It's kind of CPU bound, so it's kind of slow. But it does produce relatively high fidelity sort of deformations, if you will. It also gives you more information than Isaac does. So my recommendation would be, if all of the features are not important, just do Isaac. And if some of those features are important, do Drake.
Well, for example, do you get good force feedback?
Yeah, so in the version of the Isaac that we were using, we couldn't get tangential force for some reason. I don't know why. And then if you switch your Isaac to some other Isaac, then you suddenly get that, but you don't get something else. I don't know. And then now apparently you get everything. I'm honestly having a super hard time keeping up. But it seems like give it a year, and I think it will be very, very good.
Okay.
Yeah, but I do encourage doing things in sim now. Back then it kind of sucked, but now it's much better. There's also better models now. Tai Chi is a simulation environment that.
Like the one that made it seem.
Tai Chi was the CMU?
No. There's Genesis that's based
Oh.
on Tai Chi that they write a robot and physics simulator.
I see. I'm not going to recommend Genesis because I know nothing about it and I've heard some things. I don't know how much of any of those. Sure, it's probably great. It's probably great. But Tai Chi, I've seen some people use it, even though it produces physically implausible interact. So it just violates physics. In your face, it will violate physics. But it's not that bad. It might be good enough. It might be good enough for again, the simulator we used for tactile stuff was super dumb, and it was good enough to get perception capabilities. So yeah, it doesn't have to be high quality. It just needs to be good enough. And I think Tai Chi is better than Tai Chi is good, and NVIDIA's is really good. Drake is really good. Yeah.
I have a low level and a high level question. Low level, when you were showing some of the experiments on hardware, for example the P swooping, the robot looked really slow.
Yeah.
How fast do you run these algorithms, and what's the bottleneck?
Controls. We suck at controls. That one was really finicky to get working because you couldn't push too hard because the other robot couldn't hold the walk. The walk was really heavy. So it kind of needed to balance it, and we had to have this kind of a sensitive control that would be going slow, no dynamics, nothing too crazy. Our perception is faster than our controls loop right now. That won't be the future, I think, for long, but yeah.
Got it. And then the high-level question, which I think is actually related to the prior discussion. So for example, when you're learning these tactile dynamics models, or in general, any of these, how do you eval? How do you know that you've got a good model?
Yeah, I have no idea. The honest truth is I think everyone in world models business, they just get as big of a data set they can. They just train their model, and then if it's not good enough, they get a bit more data, and if it's good enough, they don't scale back. They're just this is the data set I have. I think the most important thing, in my experience, to get right is these tactile encoders. So pre-training those is also usually a really good idea. If you
pre-train them on natural images, not.
No, you pre-train them on
Also
reconstruction tasks. So now with advances like Sparsh, which is this really good tool from FAIR, that might not be a huge problem. And I think within the last year, there's been 4 papers in this space. There was T3 from Ted Ellison's group, who's done pre-training on massive scale, massive touch sensors. We've done some work. Meta's done some work. So, but that seems to be the painful part. Everything else is pretty stock standard world model learning. Great question. Thank you, Zach.
There's nobody else. Yeah, so I wanted to poke at a little bit, here, for example, membrane dynamics model. Is there any first principles physics in any of this, or is this all data driven?
It's all data driven.
And then I guess kind of building on that and kind of what you just asked, do you see a place for first principles physics in these things? It seems like we're going this extremely data driven route where it's unclear to me also as compute's scaling up, it feels like we should be able to simulate everything. We should be able to do all the, FEA, FEM. We should be able to do all this soft stuff, no problem with the amount of compute we have now. And at a certain point, it feels like for a lot of these tasks where data collection's hard, that like we maybe should be investing more in the first principles physics for sim for some of these tasks. I don't know, just general thoughts on this, like
Yeah.
where the field is going, and like maybe if you see openings for more physics in some of these things.
There's a ton of openings in more physics. I think that most people don't know how to do it. I'd say it sounds like kind of harsh, but it's kind of true. Like the most recent progress on this problem, like this exact problem you're describing, is TAC-SL from NVIDIA. So they have this like sort of an integration module into their Isaac thing that is like a very sort of a loose simulation of tactile sensor dynamics for one particular tactile sensor. And it's pretty good. Like we have like one paper under submission which is doing like zero shot sim to real 3D representations from that feedback. So I think the hard part is that most people that do robot learning are not like dynamicists or modelers in any way. So like it's
I
just
think by the same token, you could make the other opposite argument, right? People who are doing like hardcore finite element modeling of these things are not good at, learning and data-driven stuff, right? So
yeah.
feels like an opportunity in there somewhere.
There's a ton of opportunity. I think the one opportunity that like I think literally no one is working on because no one knows how to do is in this task. Like I'm sure there's a way to like write controllability. Like how do you know I can get to that green configuration? I have no idea. We just like kind of YOLO things. I mean, it's true. Like I wish I had something more academic to say, but we just tried things and like it could do like some range, like some pretty large range. It could do like 110 degrees, I think, pivots, which is pretty impressive. But I don't know why it's 110. It's not like 80, right? I have no certificates to tell you anything. And to Andrea's point, like we just learned models and it worked. There's like it's like if you could do your like pixels to certifiable controls work here, like this would be like the perfect application of that idea when you have extrinsic contact, right? Like almost everything we do is pretty YOLO.
Yeah. I mean,
It's like NPC, but like if you get it wrong, like you're kind of hosed. I mean, that's true.
checks out. Thanks.
Yeah. Yes.
Thanks for the great talk. Just a low-level question. How do you model the tool we show the dense correspondence, like the different bending angle thing?
Oh, the model is this thing. Oh, sorry. I'm just going to jump forward. Oh. One more. One more. Bang. So this is the model. And so what we do in this model is we apply sort of a force to the tip, and that will produce these sort of deltas, and we basically just apply those deltas to the object and deform it. And then we just paint where the points end up being in 3D space. So these are, once I apply the delta to my painted points, I just see where they end up going.
Yeah, I'm just thinking because here we are considering the compliant objects, right, or the deformable. So I'm not sure whether like methods like skinning ways or something that introduce some like soft things among the points would help. Is that like pure 3D representation? Because for rigid body that works.
Sure.
But for compliant, for example, for the rightmost case, it doesn't have any correspondence or the information of like, when object compliant moves, we have the linkage or connections. So
That would be
sure.
super cool.
Yeah.
If you could do that, that would be super cool. I don't know how to do that in a differentiable way, but I'm sure there's probably an approach, and you would just embed that in there, and I think it'll work better. Yeah, I think that would be really cool.
I'm just trying to think of ways to model objects and
Yeah.
interactions, so I think that would be
That's a
interesting.
really great idea. I think the other thing to kind of think about as you were describing is there's other works that have extended this idea of these SDF learning approaches, like something called Bacon. I don't know why it's called Bacon either. These names are just wild. But they've figured out ways of modulating the frequency bandwidth of these networks. So the ReLU kind of architectures that we're using, they're like the worst kind in terms of like feature fidelity. So if you kind of like look carefully at that thing, kind of the edges are a little blurry. It's not as sharp as it should be, and there's like ways of making like these reconstructions much sharper by allocating different amounts of frequency content in the representation itself. And if you can put some artificial ways of like pushing points to like follow the correct paths, I think you can get like super high fidelity reconstruction. Those would be really powerful for graphics. Like you could totally like have like a really cool metaverse, kind of like a omniverse thing going on. That would be really, really nice. For robotics applications, I'm not sure if you need that much work. But for like engineering stuff, that would be really, really cool. I hope you don't do this to your spatula. Oh yeah, sorry. Yeah.
I have a question about the, if you learn the contacting mode of dynamics, can you solve MPC optimization to solve a sequence of actions to do a very fast control?
Not sure about very fast.
Because, like thinking if you're doing a dynamic task like hand spinning or fire jungling, if we have a very good dynamics you have learned from the data set, can we just do optimization to solve a sequence of action to do these challenging dynamic controls?
Yeah, I think that's a really, really great question. I think it's a very deep question of like, I even view that question as like, should you use a model for some of those things? So like very dynamics tasks like cracking a whip, twiddling a pen between your fingers. Some of these are very, very hard to capture in a model-based perspective. And if you look at people, they often also have very poor models of how these things work. They just kind of like learn from almost like what you would think of as RL or behavior cloning. There's not like a particularly explicit model. They just kind of like crack the whip a few times and like, oh, I get it. So
like the human instinct that we just born natural how to control and do these tasks.
I feel like it's closer to how RL works. Like I think when I think of how Xi Qi's work with Jatinder Malik, I think that those kinds of approaches where if you're looking for these super fine sensory motor skills that require lots of breaking and making contact, maybe model-based sort of perspectives there where the object dynamics matter a lot is in terms of deformation might not be applicable, and more of like a sensory motor, like fast loops are a better tool. Yeah, like I just imagine that like there's sort of very deliberate, slower manipulation skills, and there's like really fast dynamic manipulation skills. And these are like better suited for RL style approaches and sensory motor loops. Whereas these are more like suited for like slow reasoning, type 1 thinking, if you will. So I'm not sure if my tools would apply there, and that's okay, I think. Cool. Thank you.
Thanks again to Nima.
Yay.